Alright, so here's the question. Prove that if A is an invertible matrix and V is an eigenvector of A with eigenvalue lambda, then V is also an eigenvector of A inverse with eigenvalue lambda inverse. So what this comes down to prove is basically you have to know what the meanings of invertible and eigenvectors and eigenvalues are. So if we say A is an invertible matrix, that means that A inverse exists. So not every matrix has an inverse that actually exists. But if we say that it's an invertible matrix, then the inverse then does exist. So we know this is true, and if the inverse exists, then the property where the matrix A times A inverse will equal the identity matrix, right? Or we could also say that it could go the other way around, where A inverse times A is the identity matrix. And basically that's the whole purpose of having an invertible matrix. So then we get to eigenvectors and eigenvalues. So this can be stated like this. So you take matrix A times V. Now V is an eigenvector, that's what we're told. Therefore, A times V will equal lambda times V. And the important thing to understand here is that lambda is just a number. It's not a vector or a matrix. It's just a number by itself. So starting from this, which is essentially, you could kind of call it the definition of an eigenvector, eigenvalue. It's not exactly a definition, but this is what it means when you have eigenvectors and eigenvalues. So using this, I'm just going to multiply each side of the equation by A inverse. And this is matrix multiplication, so we do have to be careful that we multiply on the same side. So in other words, on both of these I have to multiply A inverse on the left side. If I were to move this one to the right, it would be, presumably it may not be equal. So we got to be careful about that. Now you notice this first one, this is the reason we did this. We can take advantage of A inverse times A from the definition up here is the identity matrix times V. And here on this side, notice that lambda is not a matrix, it's not a vector. It's just a number. So this number can easily be moved out front of A inverse without changing the result at all. So we can say that this is equal to lambda times A inverse times V. Now, the identity matrix times V, well, times anything just returns whatever it's multiplying. So that's V equals lambda A inverse V. Now, again, lambda is just a number. So even though you can't do division with matrices or vectors, it's okay to actually divide a number. So I can divide lambda, and then I'll get 1 over lambda times V. Oh, let me go back. That lambda's pretty scribbly. 1 over lambda times V equals A inverse times V. By the way, 1 over lambda, here's the little trick, I guess, here is that the inverse of a number is just 1 over that number, right? So this is lambda inverse times V equals A inverse times V. And that's what you were asked to prove. So prove that if A is an invertible matrix, yada yada yada, then V is also an eigenvector. V is an eigenvector, like this, of A inverse, with eigenvalue lambda inverse. And that's exactly what we see. If it's a little confusing to look at it that way, you can just flip the equation around. You get A inverse V equals lambda inverse V. And if you were to compare this with the basic meaning of eigenvectors, eigenvalues, V is still your eigenvector, just like it was up here, but now you have lambda inverse as your eigenvalue and A inverse as the actual matrix. And there you go. That's how you would prove it.